All right. Hello, Laia. Why don't we get started with you telling me a little bit about your background and what got you into this field?
Sure. So my dream has always been to apply my skills as a physicist and a mathematician to solve relevant problems, to provide value to society. So that's why I started by learning data science and machine learning. I worked as a data scientist. I also did some projects in the industry. And then I discovered quantum technologies, especially quantum computing. And I realized that I could mix classical machine learning with quantum machine learning to get the best of both worlds. And I literally fell in love with quantum computing. So I decided to do my PhD on quantum machine learning. And I've been studying different algorithms and how they can be applied to solve relevant problems. So yeah, that's what I've been doing, and I'm enjoying it very much to now.
That's amazing. Tell me a little bit more about the specific project you've been working on, right? Because you've really spanned across several different things across the general theme of quantum machine learning, right? You want to tell me a little bit more about that?
Yes. So the first project I did, it was on quantum error correction. So as you know, the hardware is not perfect, and when you run a quantum algorithm and you apply a quantum operation, there's going to be some noise after this quantum operation, so that the result of your algorithm is noisy and the results are not precise. So one of the challenges in quantum is to be able to correct these errors so that the quantum algorithms are more reliable. So I actually worked on a project which consisted on applying classical machine learning to find optimal strategies to correct these quantum errors after they happen during the execution of a quantum algorithm. So I used a technique called reinforcement learning, which was able to find good and optimal strategies to apply some corrections to correct these quantum errors. So that's the first project. The second project I did was in the field of molecular chemistry. So we wanted to find excited properties of molecules, such as the excited energy or the dipolar momentum. The problem with molecular data is that when the number of of atoms increases, the molecule becomes more complex, and you need more computational power to get the properties of the molecule. So at some point, if you have many atoms, it's not possible to run classical algorithms to study these molecules. So here I was using a quantum algorithm which uses random quantum circuits from a certain family. So you define the quantum operations that you can do, and then you randomly choose these operations, and you use these random quantum circuits to extract useful features from your molecular data, and then you fit this into classical machine learning model to obtain your predictions. And the good thing about these algorithms is that it scales better with the number of atoms of the molecules, so that eventually you will be able to study more complex molecules that you would not be able to do that with classical technologies. And the good thing about this algorithm is that it's super flexible. So I've also applied this algorithm to very different data. So I focus on time series, and I was able to predict financial market and also agricultural products prices. So
Such a
using the
diverse
same,
application.
yeah, exactly, using the same algorithm, I could study molecules and predict financial markets and also prices of vegetables. And we did a collaboration with a company which is called Growing Data, which is a consulting firm that uses machine learning for agricultural problems. So yeah, I really like this algorithm because it's super flexible.
That's amazing. And you touched a little bit on it here, but what is the broader value that you see quantum bringing to industry, right? Because there's a lot being done on the academic side. How do you see that transferring over into industry and having kind of that downstream impact?
Okay, I think there are a lot of applications in quantum computing. I think quantum computing is going to allow to reduce CO2 emissions. Also, it's going to make companies adapt themselves to be more climate friendly. It's also going to help us into the drug discovery process so that patients can have more reliable medicine and have access to this medicine faster. And I also think in the field of oncology and cancer detection, there are a lot of applications of quantum technology that can help speed up these fields. And of course, it's not that we're going to replace every single classical algorithm by a quantum version of it, but we're going to use for the use cases where quantum can really help and really provide a speed up. So I think there's a lot of room for that.
Actually, can you dig a little bit more into that? Because I think there's a common misconception for people that maybe don't go deep in quantum yet, have heard generally about it and know it's coming, but still feel like it's, years away because of the hardware scale up. Can you talk about some of the clever engineering solutions and kind of the quantum inspired models that you're working on that help, almost as a stepping stone to that full adoption as the hardware matures?
Yeah, now that you say that, I think that the problem with this is that quantum became very popular when some algorithms were discovered, like the Shor algorithm that would allow to crack the classical cryptography system. So people had very high expectations with quantum technologies. And then scientists say, well, these algorithms are very nice, but we're not going to be able to implement them in the current hardware or in the short term. So people became more skeptical. But I think that not being able to crack cryptography is not a real problem because there are a lot of other things that can be done with the current hardware or even with quantum simulation. That's what you were talking about, quantum inspired algorithms. So there's a whole new field which is called NISQ, which means near intermediate scale quantum, which tries to build algorithms with the hardware that we have today or with the hardware that we're going to have in the next few years. And there are a lot of applications for that. And talking about quantum inspired algorithms or in generally inspired algorithms, there are a lot of algorithms that are inspired in biological systems. So, for instance, there are the genetic algorithms, or there's one algorithm that I particularly like, which is called particle swarm optimization, which uses the knowledge of how ants move and communicate with each other to find optimal paths to find food. And this is an optimization algorithm, a classical optimization algorithm that it's used a lot. And of course, when we use this algorithm, we're not using actual ants to do that. So we're just using the idea of how these ants behave to provide value to this algorithm. So the same can happen with quantum technologies. We don't really need to always use the hardware to get advantage because we can build some algorithms which are inspired by how quantum physics work so that we can use that to our advantage. And there's an algorithm in edge detection, for instance, that you can run using the classical using classical computers, but use the knowledge of quantum physics to get a better result. And there are a lot of algorithms with that. We're now building within Genai an algorithm on drug discovery where we're using quantum filters. So it's a type of quantum image processing to get some useful filters from our data that are then fed to a classical machine learning algorithm. And we do not need to use the actual hardware right now. It is true that when the hardware improves, we're going to scale our solutions to get the most of them. So when we're able to use the current hardware, we're going to use it. And it's not that we can never use it. There are also solutions that can be run today on a quantum computer. At InGenI, you're building this climate change um, algorithm where you're using the actual hardware, you're using quantum annealing, and it's running on current hardware. And this algorithm could not be possible to run on classical computers. So there's a lot of things that we can do today.
And that's where we have the impact, right? That's where, thinking about all of these high impact areas where we've got, raging pandemics and climate change and, lack of efficient precision therapies, right? All of these areas where I feel like there's such an opportunity for quantum to be just such a paradigm shifting type of technology and really transform all of the life and environmental sciences. And I think these stepping stones that's what excites me the most, right? Being able to accelerate, the adoption of some of these technologies and getting the power of this tooling into the hands of these people that are doing that high impact work, right? And it's not necessarily 10 years from now, right? There are ways to, look at this, and that's really what I hope we can see through in the few use cases that we're working on, is to really start more intimately understanding. You mentioned actually on the 3D CNN algo you're working on right now, how deep do you take the abstraction? How much do you simplify? Where do you draw the line? And I think there's a lot that we're kind of pulling together as far as the engineering and where we can really, help there. And I think that that's really, it's exciting to kind of see these all the way through.
Yeah, and it's not just like quantum computers run faster than classical computers. We're not going to replace our personal laptops by quantum computers.
Right.
It doesn't work this way. It's just a new paradigm of computation, a new rules of the game. And we're going to play with that. And it's not just, okay, let's run the same algorithm on a quantum computer. It doesn't work like that. You have to find use cases where quantum can provide an advantage. So I think that's also a challenge, but that's why
Yeah.
companies like Ingenai exist to make things better
And
for.
pulling together different models to make a solution, right? Because it's one thing just having a bunch of algos and not really knowing how to pull those all together, but looking from the solution backwards almost and saying, all right, let's quantize all the areas in this that we kind of can. And the oncology is kind of a perfect use case where you were looking not only at the 3D CNN algo, but how does that also transition into 2D? How do we look at the edge detection, right? And what other supportive algos are within that can be enhanced, right? And I think that's really interesting because that also shows the complexity that goes into getting an end result that has impact, right? It's not just take an algo and that solves every problem, right? It's a combination of different things that you're pulling together in a meaningful way. Would you say that you would agree with that? Is that fair?
Yeah, yeah, definitely. It really depends on the problem. But one of the good things about quantum machine learning or machine learning in general is that they're usually very applicable to different problems. So when we're working with this drug discovery project, we can use similar algorithms than if we were working with images. So when we work on an oncology project and we have cancer detection, for instance, we can reuse some parts of the algorithm to treat this very different use case. So I think
Yeah.
it's a good thing about quantum machine learning. Of course, it has to be adapted to the problem, and data scientists need to see if it makes sense to use one algorithm or not. But that's what happens with every machine learning algorithm, right?
Yeah. Yeah, it's the broad application, right? It's to your point, you can solve oncology problems, you can solve climate problems, eventually solve financial markets problems, and there is such a broad application. And I think that's what makes it so exciting is if we can start solving some of these more broadly used algorithms and giving that kind of end-to-end access in a way that's really meaningful. I feel like that will be a huge acceleration. And then also benchmarking, right? Because you talked about the error correction, you talked about the evolution of the hardware. And I think one thing from an industry side and businesses that are looking to invest in like a quantum computing adoption and roadmap and strategy, right, is being able to prove the value that that's going to bring and when they're going to unlock that advantage, right? And so being able to show that, okay, there might be a quantum inspired model that's running on simulations today. And how will that scale and how will additional advantage come through to the business as time goes on and as that hardware matures? And I think businesses need to understand more of that. And I think the more that we can also help them through learning what these benchmarks are and learning how to kind of structure that will bring a lot of value to them as well as they gain their own kind of education and understanding.
Yeah, and also these fields evolve very fast. So it's true that there are limitations on the quantum hardware. There are limitations on the number of qubits that you can use, and also on the complexity of the quantum circuits that you can use. But it's also true that there has been huge advances over the years. So these big companies that are building quantum computers, they have roadmaps, and they have been very good at following these roadmaps, and
Yeah.
they're not easy to follow.
Which is
Like,
not easy, right? Tech
yeah,
always
exactly.
fails. So
Like,
you
it's
gotta
not
give
easy
them.
in general. But yeah, I think especially in quantum, you never know what you're going to get. It's a new field of research, right? So I think that there are expectations. There's hope for the quantum to advance fast, and then we will be able to scale these solutions as the hardware advances.
Yeah, and hopefully see some promising speed ups, which I know we're doing a lot of testing and trying to be able to prove a lot of that ourselves. And so it'll be interesting as we continue to push through results and see how see how everything is performing. Um, but more on the personal side, tell me a little bit more about your fellowship and also where you're from and a little bit more about your background.
Yeah, I'm from Spain. I'm from Barcelona, and now I'm doing my PhD in Madrid, also in Spain. And I'm doing my PhD at the Autonomous University of Madrid, and I have a private fellowship, which is from La Caixa Foundation.
Amazing. Yeah, that's
Yeah,
that's really awesome. Tell me more about the drug discovery project you're working on with Ingenai.
sure. Okay, so the goal of this project is to cut expenses and, most importantly, cut training times for the early stages of drug discovery. So before the drug goes into clinical trials. So the idea is that when a new molecule is proposed, we want to have as much information about this molecule before we actually put it on people's bodies,
Yeah.
right? And we
Hmm.
want to speed up this process so that it gets faster to the patient. So there are a lot of things that have to be taken into account to do that. And we're doing a particular project where we're trying to predict what it's called the binding affinity between a drug and a protein. So when you have a new drug and you put it into a patient's body, it's going to bind some protein of this patient in order to do its function. The thing is that you want the drug to bind a specific protein and not bind other proteins, because if it binds other proteins, then it might cause side effects. So the binding affinity measures the strength of the interaction between a drug and the possible proteins that it might encounter. And it's not easy to predict this quantity because it depends on a lot of factors. Like, it's not only the composition of the drug, it's not only the atoms that form this drug or the proteins, but there are like outside interactions that can affect how this protein and drug will behave. So it's not an easy task. It's not easy to just do a biological model and find this value. So what scientists do in these cases, they usually use machine learning, because when we have data and there's a pattern, usually machine learning is good for predicting and learning this pattern. And there are existing machine learning models which are very good at predicting this quantity. But the problem is that these models take a lot of time to train and then require a lot of resources. So this makes this process slow. And what we're trying to do at Interni is build a hybrid classical and quantum model that can help reduce the number of training parameters and then reduce the training time of these models so that we can have access to train models faster.
And how are you approaching that? What are the few things you're kind of exploring?
Okay, so we're basing this model on an existing 3D convolutional neural network, which treats the data as basically as an image, as a 3D image, if that makes sense. So imagine you have a spatial domain, like a little cube, and in every point of this cube, you can either have different types of atoms. You can have a hydrogen atom or an oxygen atom or whatever atom you can have there. And so this is your data. You're encoding the position of the different atoms of the drug and the protein, and you want to learn from that. So then we use a classical machine learning model, or there exist classical machine learning models. We use convolutional neural networks to extract features from these images and then combine them all to give a final prediction. And what we're doing here is we're going to replace some of the convolutional layers of the image by a quantum circuit. So we're going to apply quantum operations on this data. We're going to extract quantum features from this data, and we're going to combine them with the classical features that the model also learns to get the final prediction. So we're combining both the classical and quantum information to get the best of both. And by
Which is
doing
running
that,
on the classical hardware right now,
which
right? Which
it
is
is,
what brings it into the world of today, right? Something that can hopefully add value today if we see it through and can prove that it's got its advantages, right?
yeah, definitely. And right now we're running the quantum circuits in the classical hardware in quantum simulation. But as the hardware improves, we're also going to run this into the actual hardware and train different parameterized quantum circuits to get better performance.
And to the point about the industry being able to benchmark the advantages and how that unlocks, this is a perfect example of that, right? Because we can look at this simulated model, what advantages we're seeing with that today, just even on classical hardware, right? And then how does that scale up as the hardware comes online, and how much, more efficient does it become?
Yeah, basically, and keep in mind that this is a very hard problem because our data is three-dimensional. Usually when you treat with images and you apply image processing techniques, images are two-dimensional. So this problem, by definition, it's harder than other problems within the image processing field. And we're able to do something with that. So I think that's very promising.
Yeah, so it's going to be really exciting to see that through and see where we can take that, and seeing it all the way through into an actual business use case, right? Get it into the hands of a customer that can start realizing the advantages of that. I think that's going to be an exciting kind of path to kind of pull it out of the research and into an actual you know, value added use case. That's, that's what we're here to build. Laia, it was such a pleasure. Thanks so much for, talking through your journey. And for those watching, we're gonna be doing a bit of a series with these. We'll have more coming, so stay tuned.
Thank you. It's a pleasure talking with you.